Hi there, welcome to our channel where we talk about traffic operations in practice. The overall intent of this video series is to reduce the learning curve for students and entry-level engineers by providing them free and high-quality learning materials in the field of traffic operations, including highway safety and travel demand modeling. The majority of content in this work is written by Professor Jiangling. My name is Amit Kumar Singh. I'm one of the contributor of this work. I'm a licensed engineer in the state of Texas. I received my bachelor's from IIT Bombay in India and my master's from UT Austin in US. Other three contributors of this work are Priyanshu Singh, who works in the field of artificial intelligence, Nidhi Kumari, who has a background in computer science and is a programmer, and Namrata Kumari. She has a background in electrical engineering and currently she is working as data scientist. Now let's get to the main content. Now let's move to part 3 of chapter 2 where we are discussing basic concepts in traffic operation. So in part 3 we will introduce several concepts that are used in everyday job in the field of traffic operations. So most of the concepts we are going to look here are those concepts which we deal with every single day or pretty much in our day-to-day life as a traffic engineer. So before starting this part, so far we have discussed traffic flow theory concepts, speed, volume, density, different relationships, space-time graph. Then we looked into statistical model, linear regression, R-square, Z-test, T-test, and then GEH statistics, and then we went through some numerical examples on how this statistical models are built and used. Now let's go ahead and look at the next part, which is traffic volume. So all the concepts we are going to discuss here are very fundamental and are very important to understand clearly. They are used in most of the work we do as traffic engineers. So the first term is AADT, average annual daily traffic. So AADT is AADT. ADT is total number of vehicles passing through a given location on the roadway in entire year divided by number of days in the year. So usually throughout the state there are several locations where state DOTs have the permanent counters where vehicles are continuously being counted, and we sum up those number of vehicles divided by 365. That's the AADT. AADT is very important concept in field of traffic operations. The AADT is the best measure of total use of roadway because it includes the entire years of data. So AADT is free from seasonal adjustment and other kind of adjustments. Now the second one is something called average daily traffic or ADT. So when we are collecting entire year worth of data and using entire year worth of data is called ADT, average annual daily traffic. When we are collecting only few days of data, at least 24 hours, let's say 1 day, 2 day or a week of data, and then using it to calculate average daily traffic, then is called ADT. So it's important to understand the difference between ADT and ADT. So when we calculate ADT and we want to use it in several calculations, for example, ADT is mostly used in roadway design. So as a traffic engineer, we are supposed to provide this information to the roadway team, or sometimes bridge design and structural design. So when we are providing the information, sometimes when we collect data in field, we only know ADT. So when we are trying to estimate ADT, we can use this equation. So ADT is equal to ADT multiplied by seasonal factor. So multiplied by axle correction factor, which is usually done by Department of Transportation, and we do not actively use it. So ADT is ADT multiplied by seasonal factor. So seasonal factor is factor. So during summer peak, when the schools are not in session, the volume on the roadway may be lower than when the schools are in session. So the seasonal factors are monthly factors. Those adjust for the monthly variation in the average traffic. Several DOTs, for example, Florida DOT has developed a seasonal factor and they continuously update it for local regions. So that's how the AADT and ADT are defined. For most of the cases, we do not have to calculate AADT. There is a statewide AADT available uh, for most of the states. So there are systems that automatically calculate statewide AADT and is available through State Department of Transportation websites. K factor. K factor is a very important factor in the field of traffic operations. So what K factor is, let's say we are looking at the hourly volume per hourly volume for a typical day. So in morning peak the traffic goes up, then it comes down, then in evening peak it goes up, then it comes down, and in night it goes down. So what K factor is the peak hour traffic. So let's say this is my peak hour between 4 p.m. to 5 p.m. So if this is my peak hour, what K factor is the peak hour traffic divided by 24-hour traffic. So K factor gives an estimate of how severe the peak is. Usually K factor ranges between 0.7 to 0.11, and we will discuss about K factor just in a little bit more. Before discussing more about K factor, let's look into the D factor. D factor is the factor during peak hour. So if we have 24-hour counts, first we use K factor to move from 24 hours to the peak hour. Now within this peak hour, if this is the median and this is the direction of travel, now within the peak hour, let's say this is my peak direction and the number of vehicles in this direction is 1000, a number of vehicles in this direction is, let's say, 100. What D factor is the ratio of heavier direction volume divided by total volume. So in this case it will be 1000 divided by 1100. This is my D factor. D factor gives the directional distribution of volume in the peak direction. So the higher the K factor, usually the worst level of service or the worst condition are existing on the roadways, because most of the volume is concentrated within that particular hour. And higher the D factor, the worst level of service or worst condition exist on the roadway. So K factors and D factors are used to change the ADTs or ADTs, change 24 hours count into, if we take 24 hours count multiplied by K factor, we will get hourly count, and if we multiply it by D factor, then we will get the hourly count in the peak direction. So 24-hour counts multiplied by K multiplied by multiplied by D represents the something called directional design hour volume, DDHV. So directional design hour volume is what determines how good the roadway is performing. So the level of service on the roadways are usually defined based on directional design hour volumes. To get to the design hour volumes, what we can do is we can either go and collect the hourly counts in the peak direction and calculate it directly, or most of the time if we are working with planning studies, all the information we usually have is ADT, K factor and D factor. So once we have this information, we can multiply them to calculate hourly design our hourly volume or hourly volume for the peak direction peak hour. So design DDHV and based on this number our level of service will be defined. Get back to the K factor. Like I mentioned, K factor is the peak hour volume divided by 24-hour volume. So one important thing to know about K factor is K factor is obtained using year-long worth of data. We do not, even though we can calculate K factor for 24-hour volume, we do not calculate it. It's not the right way to calculate it based on 24-hour counts. Now, it's also not right to calculate it using 365 days of count data because of some research which has come out. So based on Florida Department of Transportation guidelines, on a roadway with irregular congestion during peak hour of the day, traffic count on the roadway may grossly underestimate the peak hour traffic demand. So what happens during peak hour is, if there is traffic here, then the traffic in the at the downstream, there may be some traffic that might reroute, some traffic that might come, let's say that peak hour traffic is between 4 to 5, so some people might decide to leave earlier than 4 or after 5. So hour peak hour volume at certain locations may not represent the actual demand. So in recent past, transportation agencies are moving away from using site specific K factor to statewide standard K factors. So this is a standard K factor table from Florida Department of Transportation. So if you are working in large urbanized area, then for freeway the K factor is between 8 to 9, arterials and highways 9. If there is congestion and if we are underestimating the peak hour volume, we will end up with a lower K factor than the actually what we need to use, and that will give us an impression that the roadway is working fine, where in reality the roadway may need some improvement. So for arterial and highways is 9, for other urbanized area for freeway is 9. So for most of them is between 8 to 9, and for urban areas for freeway is 10.5 and 10.5 here. So like I mentioned, the K factor usually lies between 0.7 to 0.11. If we go and look at the statewide maps, for example, this is a data from Texas Department of Transportation. Theoretically, the K factors are available here, 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 here. So K factors are available at all the locations, and K factor here may be 0.7, K factor here may be 0.11. Let's say we are looking at this freeway, which is Interstate 35. K factor here may be 0.9, K factor here may be 0.85. Now we are ending up with a lot of K factors, and then the question is, which K factor should we use, or should we average them out? So the guidance is to not use the site specific K factor, and thus discussion is provided here. So one big thing to remember about K factor is the K factor is the characteristic of a population in a region. K factor comes from the fact that within a region, most of the people go to work during certain hours, they come back from work during certain hours, and that's kind of an overall picture of what constitutes the value of K factor. And this is a regional number, more or less. So also it depends on the facility type, but this is kind of a more regional driver characteristic. Whereas the D factor is calculated based on site specific data. So there may be roadway which is one way, people may be going from this direction but taking another route when they are coming back. So D factor is calculated for sites specific locations, and which is mentioned here. So K factor is typically a single number for entire project. That's very, very important. So what I have seen is on many projects people use calculate different K factor from different maps, for example different K factors from different locations, and then they either take the maximum or average them out or take the one of the upper numbers. How ideally we should be only using the K factor as a single number and not use the K factor which are spread out through the network. Whereas D factor varies significantly based on the roadway type and roadway location. So for K factor, even though K factor here is different, K factor here is different, here is different, we should not use different K factors. Usually we need to come up with one single K factor for entire project. That's very, very important and a common mistake that happens in practice. Whereas the D factor needs to be calculated based on the roadway type and location and based on the data we are collecting. For most of the cases, if we are not collecting data, then we have the AADT, K factor and D factor from the statewide maps. So an important discussion here about K factor and D factor. Overall, K factor should not be calculated by hand, it should be calculated by agencies because of the way demands are restricted in the system. And then even though there are different K factors we are calculating for different locations, we should be ideally using only one K factor for entire project, or or if the project is really long, then for a homogeneous section at least we should be using the same K factor. So ideally, let's say within 10 miles we should not be changing the K factors. Hourly variation of traffic demand volume. This is another important concept. So we have discussed about the directional design hour volume already. So let's look at hourly variation of traffic demand volume. Like I mentioned, in the morning peak the traffic goes up, and in evening peak usually it goes higher than the morning peak. So this is a typical volume profile when we collect the data for 24 hours. This is a typical profile we get. So if we are looking at the peak hour here during morning, this is called AM peak hour, and during afternoon this is called PM peak hour. But when we do simulation or travel demand modeling, then we look on the both sides of the peak and before the congestion sets in. So these hours which are used in analysis are called AM peak period. AM peak period is different than AM peak hour and is very important to remember. So there is a conversion factor that converts the peak periods to peak hours in travel demand models. So peak periods are typically multi-hour morning and evening rush hours. Traffic counts collected on a congested roadway can be much lower than actual traffic demand on the roadway. Therefore, counts from a single peak hour may or may not accurately reflect the traffic demand for the roadway. So let's say during 3 to 4 p.m. there were 1000 vehicles, and 4 to 5 p.m. let's say there were 1500 vehicles, and let's say the capacity of the roadway is around 1500, and then let's say between 5 to 6 p.m. the observed traffic is around 700 vehicles. So when we are looking at peak hour only, we might get an impression that the peak hour volume is 1500. However, what it might have happened that the capacity of roadway is 1500, so some of the vehicles are stuck and they have moved to the next hour. So out of this 700, if these vehicles were not stuck, this might have been 1800 and this might have been 400 only. So that's why the peak period is very important. So one of the use of peak period is to capture the volumes that are stuck in the traffic before and after the peak hour. Even though we are not going to capture everything because some of the vehicles will reroute through another roadway, and we will talk about it soon. Peak hour are 1 hour interval that are used to evaluate the performance of roadway. So majority of time in our traffic operation career we are dealing with peak hour only. Peak hour is what defines everything. So what we do is we look at one of the worst hours. Usually we look at AM and PM because the directionality is different during AM and PM. So we looked at during AM peak and PM peak. These are like one of the worst hours for the traffic. So based on the what is going on in AM and PM peak, our level of service on the roadways are defined. So peak hours are 1 hour interval that are used to evaluate performance of a roadway. Let's discuss traffic count versus traffic volume next. So in traffic operations, this is one of the most complex, most challenging uh, concept in terms of practical importance. So this is something we face in our everyday life. It's one of the most challenging to uh, adjust to, and it's kind of most challenging to deal with. So the difference between traffic count and traffic volume is probably one of the biggest challenge we have in traffic operations, or one of the most important aspect of traffic operations that a traffic engineer must know and understand. So let me draw this street here. So what this figure 2.8 is representing is there is a freeway moving from left to right in this direction. There are cross streets 1, 2, 3, 4, 5, 4, 5. Let's call this street 1. Let's call this street 2, street 3, street 4, street 5. Since, like I mentioned, this is one of the most challenging aspect in traffic operations we have to deal with, let's spend 10 to 15 minutes on this topic and move a little bit slowly. So this is my arterial here, and let's say during peak hour there is a lot of traffic here. So there is an entrance ramp which has caused bottleneck here, and downstream of it there are some vehicles which are moving almost freely. Now if a vehicle which is here wants to go to this cross street in this direction, his or her preferred route would be to go straight on the freeway, take the exit ramp here. So let's say there are exit ramps here, there is one exit ramp here, one entrance, then another entrance ramp. So this is ramp 1, this is ramp 2, this is ramp 3, there is another exit, this is ramp 4, this is ramp 5. So the preferred route in the absence of traffic would be to go straight and take this exit and then go here. However, since there is a big bottleneck, the driver may behave differently. So that's where the concept of traffic counts versus traffic volume or traffic demand comes in. So ideally, if we are working on this project, what we do is we go in the field and collect the counts. So we usually collect 24-hour counts, then we figure out the peak hours, and then we look at the counts during peak hour. So if I'm working on a project, typically what an traffic engineer will do is he will look at the peak hour, then figure out what was the volume on the freeway here. Let's say this is a freeway. What was the volume here, 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 here. So this is the same figure down below. And then what is the volume here, here, here at these intersections. Now, once we collect this data, this is called counts. Typically what we do is we try to simulate these counts in the softwares. For example, Synchro, if I'm analyzing this particular intersection in Synchro, then I will go and feed in the volumes and try to see how this signal is operating. So if there are a lot of vehicles at this intersection, the signal might fail in Synchro. Or if I'm working on a Visim project, then I will try to match the volume that I have observed in the field during that peak hour. Let's call the peak hour is between 4 to 5 p.m. Now the issue with using the counts is the counts do not reflect the actual expected number of vehicles that were anticipated there. So ideally, when we are working on traffic models, what we should be inputting is traffic volume or traffic demand. Traffic volume. This is what we need to enter in the traffic simulations. So let's say there is a signal here, and in the absence of many influence, there is 400 vehicles in this approach. This is the traffic volume or traffic demand for this approach. However, since there are various things happening at different part of the network, this volume may be lower or higher. So that's the one of the biggest challenge in the field of traffic operations, is how do we handle the volume versus counts. Because we cannot observe the volume, we can only estimate it or try to take a educated guess. And the thing what we can do is we can collect the counts. Typically for most of the projects we see in our career, the counts are collected, then they are fed into simulation model, and we are trying to change the simulation settings such that the model is matching the counts. That's all we do. And then after model is matching the counts, then we do the improvements and say, okay, based on these improvements and this will happen. However, ideally we should not be using the counts as the basis. Ideally we should be using the demand or the volume, but there is no way of knowing the demand, the actual demand, because the only thing which we can observe is the count. So that's where one of the biggest challenge in traffic operations comes from. So let's look at this challenge a little bit more deeper before we start thinking about the solutions. So well, let me reload this again. I will draw this street again. So we have a freeway here, then we have an arterial here, and then we have 5 streets, 2, 3, 4, 5, and let's say this part is congested. Now what uh, the first thing that can happen is the metered flow. So let's say there is a congestion here, and only 2000 vehicle per hour can pass through this point. So the downstream of it, is likelihood that the number of vehicles, if we measure the flow here, it might be 1800. If we measure the flow here, it might be like 1600. That does not mean that the need at this hour at uh, at this location is only 1600. However, in majority of the projects we go and observe the counts and we try to simulate the counts, because it's very tricky to actually calculate the volume. So the first thing that can happen is, due to congestions, the volume we have measured or look at the field is metered. There is no direct way of measuring the demand or the volume. So the only thing we can observe again is the count, and once we observe the count, it might be metered. The second thing that can happen is traffic diversion on the nearby roadway. For example, if there is a vehicle here who wants to go to street number 5, let's call it street number 1, 2, 3, 4, 5. So instead of going through freeway and taking the exit ramp here, the vehicle may decide to uh, exit here or go straight. Or there are some vehicles who may decide to exit here, then take the entrance here, exit here, then go here, go here. Now because of this diversion, we'll notice that the number of vehicles in this area and number of vehicles at this intersection has increased, whereas number of vehicles on the main lane has decreased. So this is called diversion. The first one is bottleneck, where vehicles are just waiting but they are not diverted to somewhere else. So the first one is metered flow. For example, if there are no alternate routes, vehicle will be stuck. So the first one is, let's say the demand is 3000 but there is bottleneck, so some vehicles are stuck here, then extra vehicles are just getting backed up. So the demand was 3000 vehicles, but we are observing the flow of, let's say, 1800 vehicles only, because they are stuck, they are still waiting to move. That's called metered flow. Then second one is diversion. If there is an alternate route for this congested vehicles waiting, they might choose to divert somewhere else. Then once the diversion happen, there are extra vehicles that would not be there if this problem is fixed. Now the third one is trip time change. Let's say this congestion happens between 4 p.m. to 5 p.m. So some vehicles may choose to leave early, let's say at 3 p.m. just to avoid this congestion, and some vehicles who are leaving around 4:45, let's say they decide to leave around 6 p.m. just to avoid this congestion. So when there is a congestion on the roadway, then there are multiple uh, simultaneous things happen: metered flow, traffic diversion, trip time change. And once we fix this congestion, then let's say there are observed flow here is 2000, and once we fix this issue, now there will be more vehicles, because people who are living at 6 p.m. during congestion might start to live at 5 p.m., which is their preferred time. People who are diverting through this route might start to use the freeway again, and people who are vehicles who are stuck here might will start to move freely. So when we are working on traffic simulations, we should be modeling our system such that it handles the traffic volume or demand. So traffic volume here is equivalent to traffic demand. So when we are modeling the system, ideally we should be looking at traffic volume, and traffic count is one of the way to reach to traffic volume. However, it's impossible to actually go and collect traffic volumes. There is no practical way in a congested system to uh, calculate traffic volume. What we can do is we can do some analysis or take educated guess to reach to traffic volumes, but only thing we can observe is traffic count. So one of the biggest thing in traffic operations to remember is common practice in traffic engineering is to replicate the traffic count and existing conditions within the traffic area. So there are two things: one is existing existing counts, and existing traffic conditions. So for example, let's say I'm only looking at street 1, signal 1, and now I'm observing a lot of queue here. Ideally, uh, we should be looking at the traffic volume, but what we typically do is we look at the counts, and let's say 600 vehicles went through. So in very rare cases, out of thousands of projects, there will be only very few projects where we will actually go and reduce this number to account for this diversion. In most of the cases, we take the traffic count and simulate the intersection with the counts. So in practice, what we are trying to replicate is we are trying to build a model that is matching the existing conditions. Now the existing conditions we have collected in the field using traffic count might be distorted already. So when we are trying to build a simulation to match a distorted reality, then our simulation is somehow distorted as well. And then once we work with a distorted simulation and then we try to have some improvements, then we will end up with distorted results. For example, if this congestion is fixed, and let's say uh, there are some issues that comes up here. So let's say this congestion is fixed and the volume here increases. Now what will happen is, if in our system, since we have not fixed these issues, there will be new issues at different locations. Or if let's say this volume is pretty high and that congestion is fixed, ideally this volume will become low. But since our model is hardwired to this higher number, we will always keep this number high in the final number as in the final alternative as well. So if we have observed 500 vehicles here, in none of the alternatives we are gonna change this to 100 vehicles. This is kind of a engineer's brain is hardwired to match the reality. in the field of traffic operations. So if we are observing something, we try to build a simulation to match that observation, but we have to understand that one of the biggest challenge in traffic operation is the reality may be distorted. So if the reality is distorted because of congestion, then the simulation model we are building will be distorted by itself, and then the improvement and alternatives we are building on top of that will be based on that distorted simulation. So is an important consideration to remember. We will look at some of the solutions to this problem when we go to traffic simulations and other travel demand modeling, but there may not be a perfect solution. It's mathematically impossible to predict the actual demand given the counts, because we don't know what choices many users have made. The best thing we can do is travel demand modeling, which has its own limitations. The Probably we can try to combine the counts with travel demand modeling and come up with some sort of solutions, or then again that may be a subjective question on whether, let's say the travel demand modeling says this count needs to be 50 and we have observed 500 vehicles here. Are we going to reduce the what we have observed in field based on travel demand models? Maybe, maybe not. Depends on how good the travel demand models are. Sometimes travel demand models in itself are not good. So these are some of the very, very complex situations a traffic engineer faces, and again this needs critical thinking. There is no direct answer to this. We will try to resolve this issue in pieces as we move along, but it's very important to remember that when we go and observe uh, counts of vehicles in the field, we should not be just using the counts as the reality or the queue observed as the reality. Usually what we do is we go and observe the look at the counts, look at the travel time, look at the queue, and we try to match what is happening in reality with the simulation. But it may happen that in reality in reality what we are observing during peak hour is kind of temporary or distorted, and ideally we are looking to simulate or understand the hidden relationship or hidden travel patterns and not the distorted part of it. So in theory, we cannot just go and fix this congestion and try to see how the volume changes and collect the data again. All we have is the distorted data. Now we are trying to make sense of the reality based on this distorted data. So that's one of the biggest challenge in the field of traffic operations, which we need to be aware of. After discussing one of the biggest consideration in the field of traffic operations and something a good traffic engineer should be aware of is the difference between traffic counts and traffic demand, let's look into some more fundamental concepts. One concept we frequently use is heavy vehicles. In our practical life, we usually classify the vehicles into light, medium, and heavy. In most of the simulation models, we use different vehicle classifications by percentages. However, in HCS and Synchro, uh, we usually combine light and medium into one. So for Synchro, we consider heavy as heavy and light and medium as one. For VSIM, we code them separately. So for traffic analysis purposes, light and medium vehicles are counted as light vehicles. Now, the standard vehicle classification is ASTO classification. So state maintains a vehicle classification data at several locations, and many times when we collect data, the data classifications are not only 3 but they are 13. So there are 13 different ASTO classes. So out of this ASTO classes, the number of light vehicles is calculated by combining class 1 to 4. Number of light vehicles, uh, this is not light vehicles. So the number of medium vehicles is calculated by combining class 4 to 7, and the class 7 to 13 becomes the heavy. Class 7 to 13 becomes, sorry, 8 to 13 is the heavy vehicles. The way highway capacity manual defines the heavy vehicles is if at a given point, let's say if the number of axles touching the ground at any point is greater than uh, if the number of tires touching the ground is greater than 4, then that's defined as the heavy vehicle. So in a heavy vehicle based on highway capacity manual is defined as any vehicle with more than 4 wheels on the ground during normal operation. So if the number of wheels are greater than 4 during normal operations, then that is classified as heavy vehicles. However, for synchro analysis, we mostly look for larger trucks, and for highway capacity software, we use the SCM definition. So this is SCM definition. For example, a good example would be small buses. So whether are we going to classify small buses into heavy vehicle or not? So if I'm working on a synchro analysis on arterial, it depends on how heavily that bus is impacting the traffic. Usually they don't, so for synchro I will consider this as a light vehicle. However, when I'm working on freeway or highway capacity software, then I will look at how many tires it has, how many wheels are touching the ground, and uh, if the number of wheels typically is greater than 4, I would classify as heavy. So the definition of heavy changes based on what kind of purpose we have, what kind of softwares we are using, and how much influence that vehicle has on the overall traffic. Next concept is passenger car equivalent, is to change the heavy vehicles and medium vehicles into equivalent cars. So the level of service is defined by a single number which is called passenger car unit, PCU or PCE, passenger car equivalent. So heavy vehicles based on their influence is converted into equivalent cars. So depending on the terrain, this equivalency factor changes, but usually it's like 2.2 or 2. For medium vehicle it's like 1.3 to 1.5. So passenger car equivalent is equivalent number of heavy vehicles and equivalent number of medium vehicles plus equivalent numbers of regular car. So PCE for a mix of truck under level and rolling conditions are 2.0 and 3.0. The next one that is very important is the measure of effectiveness. Measure of effectiveness is how we define whether the roadway is working in a good condition or not. So the measure of effectiveness is usually defined based on several it's called MOEs in short. So we will hear this word several times in traffic operation, called MOEs or measure of effectiveness. Several MOEs that are used in practice are travel time, travel delay, travel speed, density, volume, throughput, intersection delay, and number of stops made. Out of these, the one which are frequently used is density, control delay, and travel time. So these two are most frequently used, and then travel time is kind of very intuitive and easier to figure out. That's why easier to digest and understand by regular public. So these three are very commonly used measure of effectiveness, with density being the most used, and then control delay for intersections. So based on the measure of effectiveness, the level of service of facility is defined. There are different thresholds to define these levels for different kind of facilities. Those are defined here. So for freeways, it's based on density. Freeway has three kind of segments: basic, merge, and weaving. These are based on density. If we are breaking freeway into individual segments, is based on density. If we are considering the entire freeway as a facility, is still based on density. So the procedure to analyze the individual segment is different than the procedure to analyze it as a facility, as we discuss later. Two-way highway class is based on average travel speed and percentage time spent following. Multi-lane highway is density, same as the freeway. Urban street segment is number of through vehicle speed, and signalized intersection, like I mentioned, is control delay. Two-way stop control is control delay, but we are only looking at the worst approach. There is no definition of level of service for two-way stop control. However, in practice, we look at the worst approach. So level of service is calculated for each lane of a given approach, and for each approach on the minor street. Level of service is not calculated for major street approach. And then all-way stop control, and then the control delay. For urban areas, the acceptable level of service is usually D. If we cross the threshold of level of service D, then we need to increase the capacity or do something to bring the level of service back in um, back to level of service D for urban areas. And typically we are working for future, so let's say we have a demand for 2050, so we need to bring that level of service under acceptable level of service for the year 2050 or 2054, depending on what is our design year. And the acceptable level of service for rural area is level of service C. This is from Texas guidelines, which kind of should be uh, common through other state as well. So these acceptable level of service are usually for the design years which are in the future. Well, that's all I have for this video. Thank you for your time. Thank you for joining us. And if you like it, please subscribe to our channel and share it with your friends.